Hello there, my name is Alar, and welcome to the Late Night Science Channel. Tonight, we're about to explore something extraordinary, something that'll completely shift how you see our place in the cosmos. We're diving deep into the Andromeda galaxy, and I'm not just talking about random facts you might have heard before. No, we're going to understand what this galaxy truly is, what it means, the sheer scale of it all. And before we get lost in the stars together, if you find yourself enjoying these peaceful journeys through space, a gentle like or subscribe would mean the world. It helps keep these late night explorations going. Now, let's begin. So picture this. On a clear night, away from all the city lights, you can actually see Andromeda with just your eyes. No telescope needed. It appears as this soft, fuzzy patch up in the sky, sitting there in the constellation that shares its name. The ancient stargazers, they noticed it too, over 1,000 years ago. A Persian astronomer back in 964, Abd el-Rahman el-Sufi, he wrote about it, called it a small cloud. He had absolutely no idea what he was really looking at. Chinese astronomers saw it even earlier, centuries before that. For the longest time, people thought it was just some nebula, a cloud of gas floating somewhere within our own corner of space. But the truth? Well, the truth turned out to be so much more incredible than anyone could have imagined. Fast forward to the 1920s, and Edwin Hubble, using this massive telescope at Mount Wilson, he managed to pick out individual stars inside that fuzzy patch. By studying these special stars, called Cepheid variables, he figured out the distance. And what he discovered was revolutionary. This wasn't some nearby gas cloud at all. This was an entire galaxy, a whole separate island of stars sitting far, far beyond the edges of the Milky Way. That moment changed everything. It opened up the universe in ways we never thought possible. Andromeda sits about 2.54 million light-years from us. Now, let me help you understand what that actually means, because these numbers can get pretty wild. Light, it's the fastest thing in existence, traveling at roughly 300,000 kilometers per second. Nothing moves quicker. In 1 year, light covers about 9.5 trillion kilometers, and we call that distance a light year. So when we say Andromeda is 2.54 million light-years away, we're talking about a distance of approximately 24 quintillion kilometers. That's a 24 with 18 zeros trailing behind it. Just absolutely massive. Here's something to wrap your mind around. Sunlight, it takes about 8 minutes and 20 seconds to reach Earth. If our sun just vanished right now, we wouldn't even know for over 8 minutes, because the light telling us it's gone would still be making its way here. Light from the nearest star beyond our sun, Proxima Centauri, takes over 4 years to arrive. But light from Andromeda, it takes 2.54 million years. Think about that for a moment. The light you're seeing when you look up at Andromeda tonight, that light left the galaxy back when early humans were just starting to figure out stone tools. Homo habilis was walking around the African savannas. Modern humans didn't even exist yet. Our entire recorded history, every civilization, every empire, every moment we've written down, all of it represents less than 0.25% of the time that light has been traveling from Andromeda to reach us right here, right now. If you could somehow hop on a spacecraft and travel at the speed of light, which is physically the fastest anything can go, you still wouldn't reach Andromeda until 2.54 million years had passed. The fastest spacecraft we've actually built, the Parker Solar Probe, it reaches speeds of about 700,000 kilometers per hour when it swoops close to the sun. At that speed, the trip would take roughly 3.9 billion years. That's nearly as long as Earth has been around. Voyager 1, launched back in 1977, humanity's most distant object out there, it's cruising at about 61,000 kilometers per hour. At Voyager speed, the trip would take over 44 billion years. That's more than 3 times the age of the entire universe. The distances we're talking about here, they're just beyond anything our everyday experience can really grasp. Andromeda is what we call a barred spiral galaxy. This means it's got this bar-shaped concentration of stars at the center, and then spiral arms reaching out from the ends of that bar. Our Milky Way actually has the same basic setup. The galaxy stretches about 220,000 light-years across. To travel from one edge to the other, even at light speed, would take longer than modern humans have walked this Earth. The Milky Way, for comparison, spans roughly 100,000 light-years. Andromeda is noticeably bigger, about 1.5 times the Milky Way's diameter based on recent measurements. Inside Andromeda, there are roughly 1 trillion stars, each one a sun, potentially with planets, moons, asteroids, all orbiting around it. Our Milky Way contains somewhere between 100 billion and 400 billion stars. Andromeda has about 2 to 3 times what we have. If you tried counting every star in Andromeda, one per second, never stopping to sleep or eat or rest, you'd need approximately 32,000 years to finish. That's longer than all of human civilization, from the first cities right up to today. The total mass of Andromeda, when you add up all the stars, all the gas, all the dust, and crucially, all the dark matter, comes to roughly 1.5 to 2 trillion times the mass of our Sun. Right at the center of this immense structure sits a supermassive black hole, weighing in at about 140 million times our Sun's mass. To put that in perspective, the black hole sitting at the heart of the Milky Way, Sagittarius A, has a mass of only about 4 million solar masses. Andromeda's central black hole is roughly 35 times heavier. There was this interesting debate for years about whether Andromeda might actually have 2 supermassive black holes at its core, based on this double structure visible in images. That theory was pretty popular in the early 2000s, but more recent observations, particularly from 2020 onward, have mostly ruled that out. What we're seeing now, the scientific consensus, points to one black hole surrounded by this eccentric disk of stars. The double structure comes from how stars orbit the black hole in this off-center, elongated disk. It's a fascinating optical trick, but not 2 black holes after all. The central bulge of Andromeda, it's enormous, spanning roughly 30,000 light-years across. That's almost a third of the entire diameter of the Milky Way. This bulge contains several hundred billion old stars, all packed into a relatively tight volume. The density of stars here is thousands of times higher than what we experience in our solar neighborhood. If you somehow lived on a planet near Andromeda's core, assuming you could survive the intense radiation flooding the area, your night sky would be transformed completely. Thousands of stars would shine bright enough to cast shadows. The combined starlight would create this perpetual twilight. True darkness would be impossible. These core stars are what astronomers call population 2 stars, the older generation, born when the galaxy was young. They're metal poor in astronomical terms, meaning they don't have many elements heavier than hydrogen and helium. These stars formed from gas that hadn't yet been enriched by previous generations of stellar death. They glow with a reddish color, characteristic of older, cooler stars. Red giants dominate the bulge, stars that have burned through their core hydrogen and swollen to enormous sizes. Some of these red giants are larger than Earth's entire orbit around the Sun. The extreme density of stars near the core creates some unique situations. Stars pass close enough to each other that gravitational interactions become common. Binary star systems can get disrupted, with one star captured by a new partner while the other gets flung away at high speed. Occasionally, stars wander too close to the central black hole. The black hole's immense tidal forces stretch the star into a long stream of gas, what astronomers call a tidal disruption event. The gas spirals into the black hole, heating to millions of degrees and emitting intense X-rays before disappearing forever beyond the event horizon. The black hole isn't particularly active right now. It's not consuming large amounts of matter, sitting in what we'd call a quiescent state. But this could change. If a large gas cloud or an entire star were to drift too close, the black hole would devour it violently. The infalling material would form an accretion disk, this swirling vortex of superheated gas. The disk would emit more light than the rest of the galaxy combined. Jets of particles might shoot outward perpendicular to the disk at nearly light speed, creating a quasar, or what's called an active galactic nucleus. Andromeda would transform from a peaceful spiral into one of the most energetic objects in the local universe. Moving outward from the bulge, we reach the spiral arms. These aren't solid structures like a pinwheel. They're density waves, regions where stars and gas temporarily bunch up as they orbit the galactic center. Think of traffic on a circular highway. Cars move at relatively constant speed, but traffic jams form and dissolve as cars bunch together, then spread out. The jam moves around the highway at a different speed than the individual cars. Spiral arms work the same way. They're waves of compression moving through the galactic disk, and stars pass through them during their orbits. The spiral arms appear bright because that's where most star formation happens. When the density wave passes through a region, it compresses the gas clouds. This compression can trigger gravitational collapse, causing the clouds to fragment and form new stars. The most massive stars born in these events shine brilliantly in blue light. These O and B-type stars are spectacularly bright, each one outshining the sun by factors of thousands or even millions. But they burn through their fuel quickly, living only a few million years before exploding as supernovae. They barely have time to drift away from where they were born before dying, which is why they stay concentrated in the spiral arms. Andromeda's spiral structure isn't perfectly symmetrical. One side looks more prominent than the other. This lopsidedness likely comes from gravitational interactions with other galaxies. About 800 million years ago, Andromeda experienced a major merger with another large galaxy. The collision disrupted the orderly spiral pattern, creating asymmetries that persist to this day. Computer simulations of galaxy mergers show it takes billions of years for disturbed structure to fully settle back into symmetry. Andromeda is still recovering from that ancient collision. Within the spiral arms lie these enormous molecular clouds, the coldest and densest regions of interstellar space. These clouds can span hundreds of light years and contain enough material to build millions of stars. The gas is primarily molecular hydrogen, along with carbon monoxide, ammonia, and more complex organic molecules. Dust grains mixed with the gas provide surfaces where molecules can form. The clouds are opaque to visible light, appearing as dark silhouettes against the background stars. But infrared telescopes can penetrate the dust, revealing the warm protostars forming inside. Star formation in Andromeda isn't evenly spread out. There's this prominent ring of enhanced star formation about 32,000 light-years from the center. This ring lights up dramatically in ultraviolet images, showing concentrations of young, hot stars. The ring's origin isn't completely understood, but it likely relates to the central bar structure. Bars can channel gas inward or outward, creating resonances at specific distances where gas accumulates and star formation intensifies. This ring contains thousands of stellar nurseries, each one a place where new suns are being born. The disk of Andromeda is where most of the galaxy's stars live. Unlike the spherical bulge and halo, the disk is remarkably flat. It's about 1,000 light-years thick at the Sun's location in the Milky Way, and Andromeda's disk has similar proportions. This flattening results from rotation. As the galaxy formed, the gas and stars that would become the disk settled into a plane perpendicular to the rotation axis. Just like pizza dough flattens when you spin it, the disk rotates, but not like a solid wheel. Different parts rotate at different speeds. Near the center, stars complete their orbits in a few tens of millions of years. Farther out, orbital periods stretch to hundreds of millions of years. In the outermost regions, a single orbit takes over 1 billion years. This differential rotation should wind the spiral arms tighter over time, like stirring honey, yet the arms persist. That's because they're density waves, not material structures. The wave pattern can maintain itself even as individual stars and gas clouds move through it. By measuring the rotation speeds at different distances from the center, astronomers can map out the galaxy's mass distribution. This is where dark matter makes its presence known. The visible matter, all the stars and gas, can't account for the rotation speeds observed in the outer regions. Stars are moving faster than they should based on the gravity from visible matter alone. Either our understanding of gravity is wrong, which seems unlikely given how well it works everywhere else, or there's additional mass we can't see. That invisible mass is dark matter, and it dominates Andromeda's mass budget. The disk also contains older stars mixed with the young ones. These are population 1 stars like our Sun, formed more recently from gas enriched with heavy elements. They've had time to drift away from the spiral arms where they were born. Some follow nearly circular orbits in the plane of the disk. Others travel on elliptical paths that carry them above and below the plane. The Sun, for instance, oscillates up and down through the Milky Way's disk as it orbits the center. Stars in Andromeda follow similar patterns. How do we actually know Andromeda is 2.54 million light-years away? This question takes us into one of astronomy's most fundamental challenges, measuring distances across space. You can't just point some measuring device at Andromeda. The distances are too vast for direct measurement. Instead, astronomers use what's called the cosmic distance ladder, a series of methods that build on each other, each reaching farther into space. The foundation starts right here in our solar system. We can measure distances to nearby objects like the Moon using radar, send a radio pulse, time how long it takes to bounce back, calculate the distance. For more distant solar system objects, we use geometry. As Earth orbits the Sun, nearby objects appear to shift position against the background stars. This shift, called parallax, lets us calculate distances using simple trigonometry. These methods give us the baseline, the astronomical unit, Earth's distance from the Sun at about 150 million kilometers. For nearby stars, parallax still works. Satellites like Hipparcos and later Gaia have measured parallaxes for billions of stars in our galaxy. But parallax only works out to a few thousand light-years. Beyond that, the shifts become too small to measure accurately. For greater distances, we need different techniques. That's where standard candles come in. A standard candle is an object whose true brightness we know. By measuring how bright it appears from Earth, we can calculate how far away it must be. It's like seeing a light bulb and knowing it's a 100-watt bulb, figuring out how far away it is based on how dim it looks. The most important standard candle for measuring distances to nearby galaxies is a type of variable star called a Cepheid. Cepheids are massive stars that pulsate, growing brighter and dimmer in a regular cycle. The key discovery, made by Henrietta Swan Leavitt in 1912, is that a Cepheid's pulsation period is directly related to its true brightness. Measure the period, and you know how bright the star really is. Compare that to how bright it appears, and you can calculate the distance. It's an elegant method that revolutionized astronomy. Edwin Hubble used this technique in the 1920s to measure the distance to Andromeda. He identified Cepheid variables in the galaxy using the 100-inch telescope at Mount Wilson Observatory. By measuring their periods and apparent brightnesses, he calculated Andromeda was roughly 900,000 light-years away.
This was an underestimate because he didn't know there are actually two types of Cepheids with different relationships between period and brightness, but it was close enough to prove Andromeda was far beyond the Milky Way. Modern measurements using the Hubble Space Telescope and improved understanding of Cepheids have refined the distance to 2.54 million light-years, with an uncertainty of only a few percent. For galaxies too distant to resolve individual Cepheids, astronomers use even brighter standard candles. Type 1a supernovae, exploding white dwarf stars, are so bright they can be seen billions of light-years away. These explosions have remarkably consistent peak brightnesses, making them excellent distance indicators. By calibrating the Type 1a supernova scale with galaxies where we know the distance from Cepheids, we can measure distances across cosmological scales. This technique helped discover that the universe's expansion is accelerating, a discovery that won the Nobel Prize in 2011. The cosmic distance ladder is like climbing a mountain. Each rung takes you higher, but you need the lower rungs to be solid, or everything above becomes uncertain. Andromeda sits on a crucial rung. It's close enough to measure accurately using Cepheids, yet far enough to serve as a calibration for more distant measurements. Understanding Andromeda's distance helps us understand the entire scale of the universe. Let's explore the lives of stars within Andromeda, because understanding how stars evolve helps us understand the galaxy itself. Stars aren't static objects. They're born, they live for millions or billions of years, and they die. Each phase contributes differently to the galaxy's appearance and evolution. Stars form in molecular clouds when gravity overcomes the pressure from gas and turbulence. A cloud fragment collapses, heating as it shrinks. When the core temperature reaches about 10 million degrees, hydrogen fusion ignites. The star has been born. What happens next depends entirely on the star's mass. Mass is destiny in stellar evolution. A star's mass at birth determines its brightness, temperature, lifetime, and ultimate fate. The smallest stars, red dwarfs with less than 40% the Sun's mass, burn hydrogen slowly and efficiently. They can live for trillions of years, far longer than the current age of the universe. Every red dwarf that has ever formed is still shining today. These stars dominate the stellar population numerically. In Andromeda, as in all galaxies, red dwarfs are the most common stars, but they're faint, contributing little to the galaxy's overall light. You need large telescopes to see individual red dwarfs, even in nearby galaxies. Medium-mass stars like our Sun live for billions of years. The Sun has been shining for about 4.6 billion years and will continue for roughly another 5 billion. During its main sequence lifetime, it fuses hydrogen in its core at a steady rate. Eventually, the core hydrogen will be exhausted. The core will contract and heat while the outer layers expand. Our star will become a red giant, swelling to roughly the orbit of Earth or Mars. After a few 100 million years as a red giant, our star will shed its outer layers in a planetary nebula, leaving behind a white dwarf core. That white dwarf will slowly cool over trillions of years, eventually becoming a black dwarf, a cold, dark cinder. Massive stars, those born with more than 8 times the Sun's mass, live fast and die young. They burn through their fuel at tremendous rates. A star 20 times our Sun's mass might live only 10 million years. These stars shine brilliantly, pumping out more light than 1 million suns. They dominate the ultraviolet output of galaxies and ionize vast nebulae around them. When they exhaust their core fuel, they don't go gently. They explode as supernovae, outshining entire galaxies for a few weeks. The core collapses, forming either a neutron star or, if massive enough, a black hole. The explosion ejects the outer layers at speeds of tens of thousands of kilometers per second, blasting enriched material back into the interstellar medium. In Andromeda right now, all these stages are occurring simultaneously. Red dwarfs are being born and will shine for eons. Medium mass stars are on the main sequence, steadily fusing hydrogen. Red giants are swelling and cooling. Planetary nebulae are expanding, their central white dwarfs exposed and fading. And somewhere, perhaps several times per century, massive stars are exploding as supernovae. Each supernova releases as much energy in a few weeks as the sun will emit over its entire 10 billion year lifetime. The energy input from supernovae drives galactic winds, heats the interstellar medium, and can trigger new star formation in nearby clouds. The chemical composition of Andromeda has changed over time due to stellar evolution. The earliest stars formed from pristine gas, mostly hydrogen and helium left over from the Big Bang. When those stars died, they returned material enriched with carbon, oxygen, neon, and heavier elements forged in their cores. Subsequent generations formed from increasingly enriched gas. Today's stars contain about 2% heavy elements by mass, enough to form rocky planets. This chemical evolution is crucial. Without it, planets like Earth couldn't exist, and neither could life. Binary stars add another layer of complexity. About half of all stars form in binary or multiple star systems. In close binaries, the stars can interact, transferring mass from one to the other. If one star evolves into a white dwarf while the other is still on the main sequence, the white dwarf can pull material from its companion. If enough material accumulates, the white dwarf's core can ignite in a runaway thermonuclear explosion, a Type 1a supernova. These are the standard candles used for cosmological distance measurements. Andromeda produces roughly one Type 1a supernova every few hundred years on average. Andromeda isn't just stars and gas. It's also filled with magnetic fields and cosmic rays, high-energy particles racing through space at nearly the speed of light. These components are invisible to optical telescopes, but play crucial roles in how the galaxy functions. Magnetic fields in galaxies are generated through what's called the dynamo effect. Moving electrically conducting fluids, in this case ionized gas orbiting the galaxy, can generate and amplify magnetic fields. Over time, the galaxy's rotation twists and stretches the field lines, building up field strength. The resulting magnetic field follows the spiral arms, with field strengths typically around 10 microgauss, about 100,000 times weaker than Earth's magnetic field. That might sound weak, but across galactic scales, these fields have significant effects. Magnetic fields provide pressure support, helping to hold up gas clouds against gravity. They also affect the motion of charged particles. Cosmic rays, which are mostly protons and atomic nuclei accelerated to tremendous energies, spiral along magnetic field lines. The fields confine cosmic rays within the galaxy, preventing them from escaping immediately into intergalactic space. This confinement is important because cosmic rays contribute energy and pressure to the interstellar medium. Where do cosmic rays come from? The primary source is supernova remnants. When a massive star explodes, the expanding shockwave can accelerate particles to incredible speeds through a process called diffusive shock acceleration. These particles become cosmic rays. Some reach energies millions of times higher than anything we can produce in particle accelerators on Earth. When cosmic rays collide with gas in the interstellar medium, they produce gamma rays and other particles. By detecting these gamma rays with satellites, astronomers can map where cosmic rays are concentrated in Andromeda. Radio telescopes also detect emission from cosmic rays. As the particles spiral through magnetic fields, they emit what's called synchrotron radiation at radio wavelengths. The radio brightness of a galaxy correlates with its star formation rate, because more supernovae means more cosmic ray acceleration. Andromeda is a strong radio source, though not as strong as some actively star-forming galaxies. The radio emission traces the spiral arms and shows where magnetic fields are strongest. Magnetic fields also affect star formation. When a molecular cloud begins to collapse, magnetic fields can provide support against gravity, slowing the collapse. For star formation to proceed, the field must somehow be weakened or removed from the core of the cloud. This might happen through a process where neutral gas gradually drifts through the ionized gas that's coupled to the magnetic field. Understanding this process is crucial for understanding why stars form at the rates they do. Scattered throughout Andromeda are thousands of nebulae, clouds of glowing gas lit up by nearby stars. These nebulae come in several varieties, each telling a different story. The most common are H2 regions, also called emission nebulae. These are clouds of hydrogen gas ionized by ultraviolet radiation from hot young stars. When ultraviolet photons strike hydrogen atoms, they knock off the electrons, ionizing the gas. Eventually, the electrons recombine with protons, emitting light at specific wavelengths. The strongest emission line is H-alpha at 656 nanometers, which gives emission nebulae their characteristic reddish color in photographs. Andromeda contains thousands of H2 regions, ranging in size from a few light-years to over 1,000 light-years across. The largest are comparable to the Tarantula Nebula in the Large Magellanic Cloud, itself one of the most massive star-forming regions in the local group. These giant H2 regions contain enough ionized gas to make thousands of stars. They're powered by clusters of O and B stars, the hottest and most luminous stars that form from massive molecular clouds. A single O star can ionize a region hundreds of light-years across. When dozens of O stars form together, as they often do, the result is a spectacular emission nebula visible across millions of light-years. Planetary nebulae are a different type of emission nebula. Despite the name, they have nothing to do with planets. The term comes from early observers who thought they looked like planet disks through small telescopes. Planetary nebulae are the ejected outer layers of dying media-mass stars. When a star, like the Sun, exhausts its core fuel and becomes a red giant, instabilities develop. The star pulsates, throwing off shells of gas. Eventually, the hot core is exposed, a young white dwarf with a surface temperature exceeding 100,000 degrees. Ultraviolet radiation from this core ionizes the surrounding gas shells, making them glow. Andromeda hosts thousands of planetary nebulae. Each one is the death announcement of a star, visible for a few tens of thousands of years before the gas disperses and becomes too faint to see. By cataloging planetary nebulae, astronomers can estimate how many medium-mass stars have died in Andromeda over the past few billion years. The shapes of planetary nebulae are often complex and beautiful, with rings, jets, and multiple shells. These structures result from the complex interplay of stellar winds, magnetic fields, and binary interactions. Many, perhaps most, planetary nebulae result from binary star systems where the companion's gravity shapes the ejected material.
Supernova remnants represent the violent deaths of massive stars. When a supernova explodes, it blasts its outer layers into space at speeds of tens of thousands of kilometers per second. This material crashes into the surrounding interstellar medium, creating a shock wave. The shock heats the gas to millions of degrees, causing it to emit X-rays. The remnant expands over thousands of years, gradually slowing and cooling. Eventually, after a few 100,000 years, the remnant fades and merges with the general interstellar medium, but not before injecting enormous amounts of energy and enriched material into the galaxy. Andromeda produces supernovae at a rate of roughly 2 to 3 per century.
combining both core collapse supernovae from massive stars and type 1a supernovae from exploding white dwarfs. Each leaves behind a remnant. Astronomers have identified dozens of supernova remnants in Andromeda using X-ray observations. The youngest and brightest are still visible in optical light as well, glowing with the energy from the explosion. Studying these remnants tells us about the explosion mechanisms, the stars that exploded, and how supernovae affect their surroundings. Reflection nebulae are clouds of dust that reflect the light of nearby stars. Unlike emission nebulae, where gas is ionized and glows on its own, reflection nebulae simply scatter starlight. They appear blue in photographs because blue light scatters more efficiently than red light, the same reason Earth's sky is blue. Reflection nebulae are typically found near young star clusters, where dust hasn't yet been cleared away. They're common in star-forming regions, often associated with the molecular clouds from which the stars formed. Dark nebulae are molecular clouds so dense and dusty that they block background starlight completely. They appear as dark patches against the brighter background of stars or emission nebulae. The most famous example in our sky is the Coalsack Nebula, but Andromeda contains thousands of such clouds. These are the sites of future star formation. Inside these dark nebulae, gravity is slowly gathering material, preparing the next generation of stars. The visible disk of Andromeda, bright and full of stars, doesn't represent the galaxy's true extent. Beyond the main disk lies an extended envelope of stars and gas reaching far into intergalactic space. This outer region is faint and difficult to detect, but it's real and substantial. The stellar halo extends to at least 500,000 light-years from the center, more than twice the radius of the visible disk. This halo contains about 1% of the galaxy's stars, but spread over such a large volume that the density is incredibly low. If the Sun were in Andromeda's outer halo, the nearest star might be hundreds of light-years away instead of the 4.2 light-years to Proxima Centauri. The night sky would be spectacularly dark, with the bright core of Andromeda dominating one part of the sky, but otherwise very few stars visible. The stars in the outer halo are almost entirely old population II stars and the remnants of disrupted satellite galaxies. When a dwarf galaxy falls into Andromeda and gets torn apart by tidal forces, its stars get scattered along its former orbit, creating a stream. Over time, these streams spread out and gradually lose their identity, merging into the general halo population. But the process takes billions of years, so at any given time, the halo is full of structure. Streams, shells, and concentrations of stars marking recent and ongoing mergers. Deep imaging surveys have mapped this structure in detail. The Pan-Andromeda Archaeological Survey used a telescope to image an enormous area around Andromeda, revealing dozens of stellar streams and shells. Each one tells a story of a smaller galaxy that came too close. By mapping these features, astronomers can reconstruct Andromeda's merger history over the past few billion years. The picture that emerges is one of ongoing growth through what we might call cosmic cannibalism. Andromeda has consumed dozens of smaller galaxies and continues to do so today. The gas also extends beyond the visible disk. Neutral hydrogen has been detected out to enormous distances using radio telescopes. The HI disk is warped, with one side extending further than the other, and the outer regions tilted relative to the inner disk. This warping is common in galaxies and often results from interactions with other galaxies or from gas falling in from intergalactic space. Andromeda's warp might be related to its past merger history or to ongoing interactions with its satellite galaxies. There's also a vast reservoir of hot ionized gas in the halo. This gas has been detected through its absorption of light from background quasars and through X-ray emission. The gas is heated to hundreds of thousands or millions of degrees by supernova explosions in the disk and by material falling into the galaxy. This hot halo contains a substantial fraction of the galaxy's normal matter, possibly as much mass as all the stars and cold gas combined. It's part of the galaxy's ecosystem, material that has been ejected from the disk by energetic processes and will eventually cool and fall back in to form new stars. Understanding the outer regions of Andromeda is crucial for understanding how galaxies acquire their mass. Galaxies don't form in isolation. They're embedded in dark matter halos and surrounded by the cosmic web, filaments of gas connecting galaxies across vast distances. Material flows along these filaments, feeding into galaxies over time. Andromeda is still pulling in material from its surroundings, gradually growing more massive. This process will continue for billions of years, though the rate is slowing as the universe expands and nearby gas reservoirs get used up. Galaxies evolve slowly by human standards. Andromeda looks essentially the same today as it did when our ancestors were painting caves 40,000 years ago. It will look essentially the same 40,000 years from now. The changes happen on scales of millions or billions of years, far too slow for individual humans to perceive. But the changes are real and significant. Consider star formation. Andromeda currently forms about 1 solar mass worth of new stars each year. That might sound like a lot, but spread across the entire galaxy, it's actually quite modest. The Milky Way forms stars at roughly the same rate, despite being smaller. This suggests Andromeda has entered a more mature phase, having already converted most of its available gas into stars during earlier, more active periods. In 1 million years, the galaxy will have formed 1 million new stars, mostly small red dwarfs with a few massive stars mixed in. That's barely noticeable against the backdrop of 1 trillion existing stars. But over 1 billion years, it adds up to 1 billion new stars, enough to make a measurable difference in the galaxy's overall brightness and mass. At the same time, stars are dying. Every year, hundreds of stars in Andromeda complete their lives. Most are medium or low-mass stars becoming white dwarfs. A few massive stars explode as supernovae. These deaths return material to the interstellar medium, enriching it with heavy elements. The balance between star formation and stellar death determines how the galaxy's stellar population evolves over time. Currently, Andromeda is forming fewer new stars than it's losing to death, meaning the average age of stars in the galaxy is slowly increasing. Andromeda is gradually aging, transitioning toward a more mature, quieter state. The merger with satellite galaxies also changes the structure slowly. Each time a dwarf galaxy is disrupted, its stars join Andromeda's halo. Over time, this builds up the halo population and adds mass to the galaxy. The process is ongoing. M32 and M110 are being torn apart right now. In a few billion years, they'll be completely absorbed. Other satellites will follow. This slow accumulation of smaller systems is how large galaxies like Andromeda grow. The approach toward the Milky Way is another slow change. The two galaxies are closing at about 110 kilometers per second. That's fast by human standards, but across 2.54 million light-years, it translates to a closing time of billions of years. Each million years, the gap shrinks by roughly 100 light-years. It's like watching paint dry on a cosmic scale. You can't see it happening, but it's inexorable. Even the orbits of stars within the galaxy change slowly. A star on an elliptical orbit gradually shifts, meaning its orientation of its orbit slowly rotates over time. Close encounters with other stars or massive gas clouds can bump orbits, nudging stars onto slightly different paths. Over hundreds of millions or billions of years, these tiny changes add up. The orbital structure of the galaxy slowly evolves, though not enough to fundamentally change the overall appearance. We've mentioned observing Andromeda across different types of light, but let's dive deeper into what each wavelength reveals. Different types of radiation come from different physical processes and show us different aspects of the galaxy. Radio waves, the longest wavelength radiation, reveal several things. The 21-centimeter line of neutral hydrogen maps the distribution of cold atomic gas. This is the most abundant form of matter in the outer disk and halo. Radio waves produced by cosmic rays spiraling through magnetic fields trace high-energy particles and magnetic field structure. Molecular emission lines, particularly from carbon monoxide, reveal the coldest, densest gas where stars form. Radio observations are valuable because radio waves pass through dust that blocks visible light, allowing us to see into regions hidden from optical telescopes. Infrared observations reveal warm dust and cool stars. Dust heated by nearby stars to temperatures of a few tens to a few hundred degrees emits strongly in the infrared. These warm dust regions mark sites of recent or ongoing star formation because young stars heat their surroundings. Infrared observations from space telescopes have beautifully mapped Andromeda's spiral arms, showing them as bright lanes filled with warm dust and star-forming regions. Infrared also reveal cool red giant stars that emit most of their light at these wavelengths. Visible light is what our eyes see. This is the radiation from stars themselves, from their surfaces. Blue and ultraviolet light comes from hot young stars. Yellow light comes from medium-temperature stars like the Sun. Red light comes from cool stars and red giants. By observing in different colors, astronomers can determine stellar temperatures and distinguish between young and old stellar populations. The spiral arms appear bright in blue light due to young stars, while the bulge appears yellowish-red from old stars. Ultraviolet radiation comes from the hottest stars, those with surface temperatures above 10,000 degrees. The most massive O and B stars emit most of their light at ultraviolet wavelengths. Ultraviolet observations highlight regions of recent star formation and show where stars are ionizing the surrounding gas, creating H2 regions. Space telescopes have mapped Andromeda in ultraviolet, revealing the intricate structure of the spiral arms and identifying thousands of star-forming regions and hot star clusters. X-rays reveal the most violent places. Gas heated to millions of degrees glows brightly in X-rays. Supernova remnants radiate intensely as their shock waves slam into surrounding material at extreme temperatures. In close binary systems, matter falling onto a neutron star or black hole converts gravitational energy into tremendous heat right before it disappears, producing powerful X-ray emission. Even the supermassive black hole at the galaxy's center can flare when it feeds. X-ray observations have mapped Andromeda in detail, exposing hundreds of X-ray binaries, remnants, and other high-energy objects. Gamma rays, the highest energy radiation, come from the most extreme processes. Cosmic ray collisions with interstellar gas produce gamma rays through particle interactions. Pulsars, rapidly spinning neutron stars, can emit beams of gamma rays, and certain types of supernovae produce radioactive isotopes that decay and emit gamma rays. Detecting gamma rays from Andromeda is challenging because they're rare and hard to focus, but space-based gamma ray telescopes have detected the galaxy, showing that high-energy processes are active there. By combining observations from all these wavelengths, astronomers build comprehensive pictures of galaxies. No single wavelength tells the whole story. Visible light shows stars, but misses hidden star formation. Radio reveals gas, but doesn't directly show stars. X-rays highlight energetic events, but miss the normal stars that make up most of the galaxy's mass. Only by observing across the entire spectrum can we truly understand Andromeda and how it works. Let's explore the gravitational forces that shape Andromeda and keep it stable over billions of years. A galaxy is held together by gravity. Every star, every gas cloud, every particle of dark matter pulls on every other component. The combined effect of all these gravitational interactions determines the galaxy's structure and evolution. At the largest scale, Andromeda sits in a gravitational well created primarily by its dark matter halo. This well is like a valley, and objects in the galaxy are rolling around in that valley. Objects near the center move quickly because the gravitational forces are strong. Objects in the outskirts move more slowly, but all are bound, unable to escape unless given enough energy. Within this overall potential, the disk of the galaxy rotates. The rotation provides support against gravity. If the disk weren't rotating, it would collapse inward. The balance between gravity pulling inward and rotation flinging things outward maintains the disk's structure. This is why galaxies have disks in the first place. During the galaxy's formation, random motions of gas clouds collided and canceled out, but the net spin couldn't be lost. The gas settled into a rotating disk perpendicular to the spin axis. The spiral arms arise from density waves, patterns that rotate through the disk at a different speed than the stars themselves. These waves are essentially pressure waves moving through the disk. They're maintained by a process where random density fluctuations in the disk get amplified by the galaxy's rotation and self-gravity. The amplified waves take the form of spiral patterns. These waves are long-lived, persisting for billions of years, even though individual stars pass through them relatively quickly. Bars, which both Andromeda and the Milky Way have, arise from gravitational instabilities in the disk. Under certain conditions, the disk becomes unstable to the formation of a bar-shaped distortion. Once formed, the bar redistributes spin, funneling gas inward or outward depending on where certain gravitational resonances occur. This affects star formation rates and patterns. Bars can also help supermassive black holes grow by channeling gas into the central regions. About 2/3 of spiral galaxies have bars, suggesting they're a natural outcome of how disk galaxies evolve. Stellar orbits in galaxies are generally not closed ellipses like planetary orbits in the solar system. The gravitational pull of a galaxy is more complex, and orbits can be chaotic or follow complex patterns. Some stars trace out rosette patterns, their orbits slowly rotating over time. Others follow what are called box orbits or loop orbits. These complex orbital patterns contribute to the overall shape and structure of the galaxy. In elliptical galaxies formed from mergers, the stellar orbits are highly randomized, which is why ellipticals have rounded shapes rather than flattened disks. Gravitational interactions between stars are generally weak because stars are so far apart. The typical separation between stars is several light years, while the stars themselves are only a few million kilometers across. The vast empty space means direct collisions are essentially impossible. But weak, distant interactions do occur over millions of orbits. These tiny gravitational tugs add up slowly, changing stellar orbits. This process operates on timescales of billions to trillions of years. More significant are encounters with massive gas clouds. A star passing near a giant molecular cloud experiences a much stronger gravitational tug because the cloud contains millions of solar masses. These encounters can noticeably alter stellar orbits. Computer simulations show that encounters with clouds can heat the stellar disk, increasing the random velocities of stars and puffing up the disk over time. This might explain why old stellar populations in galaxy disks have larger vertical heights than young populations. Satellite galaxies also disturb the main galaxy through tidal forces. As a satellite orbits Andromeda, its gravity raises tides in the disk, similar to how the Moon raises tides on Earth. These tides extract energy and spin from the satellite's orbit, causing it to slowly spiral inward. At the same time, the tides transfer energy to the disk, heating it slightly. This is a slow process, but over billions of years, it can have measurable effects on both the satellite and the main galaxy. Between the stars lies the interstellar medium, a thin soup of gas and dust that fills the galaxy. Most of this material is hydrogen, the simplest and most abundant element. Hydrogen exists in several forms throughout Andromeda. In the coldest molecular clouds, it forms molecular hydrogen. In warmer regions, it exists as neutral atomic hydrogen. Near hot stars, ultraviolet radiation strips away the electrons, ionizing it and creating glowing H2 regions. The atomic hydrogen extends far beyond the visible stellar disk. Radio telescopes operating at a wavelength of 21 centimeters can map this neutral hydrogen. The resulting maps show that Andromeda's HI disk is warped and lopsided. One side extends significantly farther than the other. High-velocity clouds of hydrogen move through the halo at speeds that don't match the normal rotation pattern. These oddities are signatures of past interactions with other galaxies. When galaxies pass near each other, tidal forces raise waves in the gas disks, much like the Moon raises tides on Earth. These tidal disturbances can persist for billions of years. The total mass of gas in Andromeda is substantial, roughly 8 billion solar masses in molecular form, plus several billion more in atomic hydrogen. That's enough raw material to build billions of additional stars. But star formation in Andromeda is proceeding at a relatively modest pace, creating only about 1 solar mass worth of stars per year. The Milky Way forms stars at roughly the same rate, despite being smaller. This suggests Andromeda has entered a more mature phase, having already converted most of its available gas into stars during earlier, more active periods. Dust represents only about 1% of the interstellar medium by mass, but it has outsized importance. Interstellar dust consists of tiny solid grains, predominantly carbon and silicates, with typical sizes around 1/10 of a micrometer. These grains form in the outer atmospheres of cool, evolved stars and in the material ejected from supernova explosions. They're blown into interstellar space by stellar winds and supernova shockwaves. The grains scatter and absorb starlight, making distant objects appear fainter and redder than they actually are. This interstellar extinction complicates distance measurements and requires careful corrections. But dust also plays crucial roles. The surfaces of dust grains provide meeting places where atoms can stick and combine into molecules. Without dust, the rich molecular chemistry observed in space couldn't occur. Dust grains also shield the interiors of molecular clouds from harsh ultraviolet radiation, allowing them to remain cold and dense enough for gravitational collapse. And dust radiates in the infrared, revealing regions of star formation hidden from optical telescopes. Infrared observations of Andromeda light up the spiral arms and the star-forming ring, showing exactly where new stars are being born. Beyond the bright disk lies the halo, a roughly spherical distribution of old stars and globular clusters extending far into space. The stellar halo is faint and diffuse, containing only about 1% of the galaxy's stellar mass. These halo stars are population 2, metal-poor relics from the early universe. They follow highly elliptical orbits that carry them far from the galactic plane before plunging back through it. Some halo stars might spend most of their time hundreds of thousands of light-years from Andromeda's center, only occasionally passing through the visible galaxy. The halo also contains stellar streams, narrow rivers of stars stretched across the sky. These streams are the torn-apart remnants of dwarf galaxies and globular clusters that ventured too close to Andromeda. The galaxy's tidal forces pulled them apart, stripping away their outer stars. The stripped stars now follow the same orbit their parent object once traveled, creating a stream. By mapping these streams, astronomers can reconstruct Andromeda's merger history. Each stream represents a past meal, a smaller system that was consumed. Globular clusters are the jewels of the halo. Andromeda hosts approximately 450 of these dense stellar cities. Each globular cluster contains hundreds of thousands of stars packed into a sphere only tens to hundreds of light-years across. The clusters are among the oldest objects in the galaxy, having formed over 12 billion years ago when the universe was young. Their stars are metal-poor, born from gas that contained mostly just hydrogen and helium. Studying globular clusters helps astronomers understand the early history of galaxy formation. The most massive globular clusters in Andromeda contain over 1 million stars. Mayall 2, also called G1, is the brightest globular cluster in Andromeda and one of the most luminous in the local group. It contains several million stars and is roughly twice as luminous as Omega Centauri, the brightest globular in the Milky Way. If you could somehow visit a planet orbiting a star in the core of G1, your night sky would be filled with thousands of stars brighter than Venus appears from Earth. Darkness would be impossible.
Globular clusters orbit Andromeda on highly elliptical paths. Some spend most of their time far out in the halo, only rarely passing through the main galaxy. Others have orbits that carry them through the disk regularly. When a globular cluster passes through the disk, interactions with gas clouds and stars can strip away its outer members. Over billions of years, these tidal interactions have whittled down some clusters, while others in safer orbits remain largely intact. The globular cluster system acts as a fossil record, preserving information about conditions in the early universe. Dark matter dominates Andromeda's mass. For every kilogram of normal matter, stars, planets, gas, and dust, there are roughly 6 kilograms of dark matter. We can't see dark matter directly because it doesn't emit, absorb, or scatter light. It doesn't interact electromagnetically at all, but we know it's there because of its gravitational effects. When astronomers measure how fast stars and gas orbit at various distances from Andromeda's center, they find something unexpected. The orbital speeds remain roughly constant, even far from the galactic center, rather than declining as they should if only visible matter were present. This flat rotation curve is the signature of dark matter. The dark matter must be distributed in an extended halo that reaches out to at least 600,000 light-years from the center, perhaps farther.
Most of Andromeda's gravitational mass resides in this dark matter halo, not in the stars and gas we can see. The visible galaxy is merely the tip of the iceberg, floating in a much larger sea of invisible matter. What is dark matter? Nobody knows for certain. It's one of the biggest mysteries in physics. It can't be made of normal atoms because we've carefully measured the abundances of elements produced in the Big Bang, and there simply isn't enough normal matter to account for dark matter's gravitational effects. Dark matter must be something else entirely, some exotic particle or particles that barely interact with normal matter except through gravity. Physicists have proposed numerous candidates, things like weakly interacting massive particles called WIMPs, axions, sterile neutrinos, and more. Experiments deep underground and at particle accelerators are searching for these particles, but so far we haven't found them. Despite its mysterious nature, dark matter plays crucial roles in galaxy formation and evolution. Without dark matter, galaxies like Andromeda couldn't exist. The dark matter halo provides the gravitational framework that holds the galaxy together. It also provides the gravity wells that captured gas in the early universe, allowing it to collapse and form stars. In a very real sense, dark matter is the foundation upon which all visible structure in the universe is built. We may not know what it is, but we know it's essential. Andromeda doesn't exist in isolation. It's accompanied by a family of smaller satellite galaxies held in orbit by its immense gravity. At least 14 satellite galaxies are currently known, though more undoubtedly remain undiscovered. These satellites range from dwarf spheroidal galaxies, containing a few billion stars, down to ultra-faint dwarfs with only a few thousand stars. They're the survivors of galaxy formation, smaller structures that formed in the early universe and were later captured by Andromeda's gravitational pull. The two largest and most famous satellites are Messier 32 and Messier 110. M32 is a compact elliptical galaxy sitting only about 24,000 light-years away from Andromeda's center, practically on top of the larger galaxy in cosmic terms. It measures roughly 8,000 light-years across and contains several billion stars. Despite its small size, M32 harbors a supermassive black hole at its center with a mass between 2 and 4 million times the Sun's mass. This is surprisingly large for such a small galaxy and suggests M32 might have once been much larger. Perhaps it was a more substantial galaxy that lost most of its stars during the close encounter with Andromeda that brought it to its current position. The tidal forces from Andromeda are slowly tearing M32 apart. The outer stars are being stripped away, pulled into Andromeda's halo. In a few billion years, M32 will likely be completely destroyed, its stars scattered and absorbed into Andromeda's stellar population. This process is happening throughout the local group. Large galaxies grow by consuming smaller ones. It's cosmic cannibalism, and it's a fundamental process in how galaxies evolve and grow over time. Messier 110, also catalogued as NGC 205, is larger but farther away, orbiting about 170,000 light-years from Andromeda's center. It's a dwarf spheroidal galaxy, elongated in shape, and containing several billion stars. Like M32, it's being disrupted by Andromeda's tidal forces. Stellar streams connect M110 to Andromeda, visible in deep photographs as faint trails of stars stretching across space. These streams are stars that have been pulled away from the dwarf galaxy, now following similar orbits around Andromeda. Eventually, all of M110's stars will join Andromeda's halo. The other satellites are smaller and fainter. Many are ultra-faint dwarf galaxies, discovered only in recent decades using sensitive cameras on large telescopes. These tiny galaxies contain only thousands to hundreds of thousands of stars, making them incredibly difficult to detect. They're often dominated by dark matter, with dark matter outweighing visible matter by factors of hundreds or even thousands. Some are almost entirely dark, with just a handful of stars sprinkled through an extended dark matter halo. These dark matter-dominated dwarfs are valuable for studying dark matter because it's the dominant component and its effects are most easily measured. One intriguing feature of Andromeda's satellite system is that many of the satellites orbit in a thin plane rather than being randomly distributed in all directions. This planar structure was initially puzzling. However, more recent thinking has converged on a likely explanation. The satellites probably formed from a single major merger event between 8 and 10 billion years ago, when a large galaxy collided with Andromeda. It was torn apart, and its debris formed the current generation of satellite galaxies. These so-called tidal dwarf galaxies would naturally lie in a plane defined by the orbit of the original intruder. This explanation fits well with other evidence that Andromeda experienced a major merger in its past. Andromeda and the Milky Way are the two dominant galaxies in our local group, and comparing them reveal both similarities and differences. Both are large barred spiral galaxies with similar structures. Both have central supermassive black holes, extensive spiral arms, stellar halos, and families of satellite galaxies. In many ways, they're twin galaxies, born at similar times from similar conditions. But Andromeda is bigger. Its diameter substantially exceeds the Milky Way's. It contains 2 to 3 times as many stars. Recent mass estimates incorporating the latest data suggest Andromeda's total mass, including dark matter, is around 1.5 to 2 trillion solar masses, while the Milky Way weighs in at approximately 1 to 1.5 trillion solar masses. There was a brief period around 2018 and 2019 when some studies suggested the Milky Way might actually be more massive, but subsequent analyses have revised those claims. Andromeda remains the more massive of the two, though not by an enormous margin. Andromeda's central black hole is substantially more massive than the Milky Way's, roughly 35 times heavier. Its stellar halo is more extensive and shows more evidence of past mergers. The major collision about 800 million years ago left its mark in stellar streams, disturbed gas distributions, and asymmetries in the spiral structure. The Milky Way has also experienced mergers with smaller galaxies, notably the Sagittarius dwarf elliptical galaxy, which is currently being torn apart as it passes through our galaxy. But Andromeda's merger history appears more violent. Star formation rates tell an interesting story. Despite being larger and more massive, Andromeda is currently forming stars at roughly the same rate as the Milky Way, around 1 solar mass per year. This suggests Andromeda has already gone through its most active star-forming phase and is now in a more mature, quieter period. The Milky Way is still relatively active. Over cosmic timescales, both galaxies are gradually converting their remaining gas into stars, but the process is slowing as the gas reservoirs deplete. If you could view both galaxies from a distance, Andromeda would appear larger and somewhat brighter, but both would be magnificent. Two grand spiral structures glowing against the darkness, island universes separated by the void of intergalactic space. But that separation is temporary. Gravity is pulling them together, and in the cosmic future, they'll merge into one. Andromeda and the Milky Way are approaching each other at approximately 110 kilometers per second, or about 68 miles per second. That's roughly 400,000 kilometers per hour. At this speed, you could circle Earth's equator in just over 6 minutes. Yet, despite this tremendous velocity, the distance between the galaxies is so vast that the collision will take billions of years to unfold. In approximately 4.5 billion years, Andromeda and the Milky Way will experience their first close encounter. But calling it a collision is somewhat misleading. When galaxies merge, the stars themselves almost never collide. Space is mostly empty, and stars are separated by vast distances. The actual probability of two stars colliding during a galaxy merger is essentially zero. What does collide is the gas. Gas clouds from both galaxies will slam into each other, compressing and heating. These collisions will trigger intense bursts of star formation, creating millions of new stars in a relatively short period. Gravitationally, the encounter will be violent. The orderly spiral structures of both galaxies will be disrupted. Stars will be flung into new chaotic orbits. Some will gain enough energy to escape the merging system entirely, becoming intergalactic wanderers, drifting through the void with no galaxy to call home. Others will sink toward the center. The two supermassive black holes will spiral inward, eventually merging into a single, even more massive black hole. This merger will release tremendous energy in the form of gravitational waves, ripples in space-time, that will propagate across the universe at the speed of light. The merger won't be instantaneous. After the first encounter, the two galaxies will pass through each other, then swing back due to their mutual gravitational attraction. They'll collide again and again, each passage further scrambling their stars and gas. This dance will continue for several billion years. Eventually, after multiple passes, the system will settle down into a single merged galaxy. Astronomers have playfully dubbed this future galaxy Milkomeda or Milkdromeda. It will be a giant elliptical galaxy, a smoothly distributed ball of stars lacking the spiral structure of either parent. Elliptical galaxies are thought to form primarily through major mergers of spiral galaxies. When spirals collide, their orderly disk structures are destroyed. The stars, which were orbiting in roughly the same plane, get scattered onto orbits with random orientations. The result is a rounded distribution. Star formation typically shuts down quickly after the merger because the violent gravitational interactions heat the remaining gas, puffing it up and making it too diffuse to collapse and form new stars. Ellipticals are often called red and dead because they contain primarily old red stars with little ongoing star formation. What about Earth? Our planet will likely survive the actual collision, though its orbit may shift because of gravitational tugs from passing stars. By the time Andromeda and the Milky Way merge, however, the Sun will already have entered its red giant phase. Roughly 5 billion years from now, it will exhaust the hydrogen in its core and start fusing hydrogen in a surrounding shell. This will cause its outer layers to swell enormously. The red giant Sun may grow large enough to swallow Mercury and Venus entirely. Earth could linger on the fringes of this expanded atmosphere, scorched, airless, and lifeless, but still physically intact. If Earth does survive in some form, the view during the merger will be spectacular. The two galaxies will fill the sky with stars, gas clouds, and glowing nebulae. New stars will blaze to life in enormous numbers. The night sky will be brilliant with light, far brighter than anything we see today. Eventually, once the merger completes, the sky will be uniformly filled with stars, rather than showing the Milky Way band we see now. It will be one of the most beautiful cosmic sights imaginable, though sadly, no humans will likely be around to witness it. Not all stars in Andromeda are the same. The galaxy contains stars of vastly different ages, masses, and chemical compositions. Astronomers classify stars into populations based on their properties. Population 1 stars are relatively young and metal-rich. In astronomical terms, metals are any elements heavier than hydrogen and helium. These stars formed from gas that had been enriched by previous generations of stellar death. When massive stars explode as supernovae, they forge heavy elements in their cores and blast them into space. This enriched material mixes with the interstellar medium and becomes part of the next generation of stars. Population 1 stars are found primarily in the galactic disk and spiral arms. They include hot blue O and B stars, medium stars like our Sun, and small red dwarfs. These stars contain roughly 2% heavy elements by mass, similar to the Sun's composition. The presence of heavy elements affects stellar structure and evolution in subtle but important ways. It also makes planets possible. Rocky planets like Earth are built from heavy elements: carbon, oxygen, silicon, iron, and others. Without previous generations of stars to create these elements, terrestrial planets couldn't exist. Population 2 stars are older and metal-poor. They formed in the early history of the galaxy, when the universe contained mostly just hydrogen and helium. Little or no heavy element enrichment had occurred yet. Population 2 stars dominate the galactic bulge and halo. They include red giants, horizontal branch stars, and the ancient stars in globular clusters. Some of these stars are over 12 billion years old, born when the universe was less than 2 billion years old. By studying population 2 stars, astronomers can probe the early history of Andromeda. Their chemical compositions preserve information about conditions in the primordial gas from which they formed. Their ages tell us when significant star formation occurred. Their distributions and velocities reveal how the galaxy assembled itself. In essence, these old stars are fossils, carrying information about a time long past. Galactic archaeology, the study of stellar populations to understand galaxy history, has become a major research field in modern astronomy. There's also a hypothetical population 3, the very first stars to form in the universe. These would have been made entirely of hydrogen and helium with absolutely zero heavy elements, because no previous stars existed to create them. Computer simulations suggest population 3 stars were massive, perhaps hundreds of times the mass of the Sun. They would have been incredibly bright and short-lived, burning through their fuel in only a few million years before exploding as supernovae or collapsing directly into black holes. These first supernovae seeded the universe with the first heavy elements, enabling all subsequent stellar generations. No population 3 stars have ever been observed. They all died billions of years ago, but their existence is inferred from the chemistry of population 2 stars, which show evidence of heavy element enrichment at very low levels.
Some globular clusters contain stars with heavy element abundances, suggesting they formed from gas enriched by only one or a few supernova explosions, possibly from population 3 stars. The search for evidence of population 3 continues, using observations of the most metal-poor stars and the most distant galaxies visible. Andromeda's stellar populations tell a story of assembly and evolution. The old halo and bulge represent the ancient past, formed during the initial collapse of the proto-galaxy. The disk built up more gradually through continued gas accretion and star formation. The spiral arms are sites of ongoing star formation, representing the galaxy's present activity. And scattered throughout are stars of intermediate ages, filling in the history between past and present. This temporal diversity makes Andromeda a living museum, displaying stars from every era of cosmic history. Everything we know about Andromeda comes from observation. Astronomers have studied the galaxy across the entire electromagnetic spectrum, from radio waves through visible light to X-rays and gamma rays. Each wavelength range reveals different physical processes and structures. One of the most ambitious projects to study Andromeda was the Panchromatic Hubble Andromeda Treasury, or PAT. Using the Hubble Space Telescope, astronomers imaged a large section of Andromeda's disk in exquisite detail, resolving individual stars. The resulting image contains over 100 million resolved stars. By measuring the brightnesses and colors of these stars, the team determined their ages and chemical compositions. This allowed them to map out star formation history across the galaxy, showing where and when stars formed over the past billions of years. The PAT survey revealed that star formation in Andromeda has varied in both space and time, with periods of intense activity interspersed with quieter epochs. Computer simulations complement observations. Astronomers use supercomputers to model galaxy formation and evolution. They simulate the collapse of dark matter halos, the infall of gas, star formation, supernova feedback, and galaxy mergers. By comparing simulated galaxies to observations, they test their understanding of the physical processes at work. Simulations of Andromeda's past mergers have reproduced many observed features, including stellar streams and asymmetries in the disk. These simulations help astronomers interpret what they see and predict what they might find with future observations. Let's think more carefully about what will happen when Andromeda and the Milky Way finally collide. Computer simulations have modeled this event in detail. About 3 to 4 billion years from now, Andromeda will fill our night sky. It will no longer be a faint smudge, but a brilliant structure spanning vast angular scales. The spiral arms will be visible to the naked eye. Individual bright stars and star clusters will stand out. It will be a magnificent sight, assuming Earth still exists and has clear skies. The first close passage will occur about 4.5 billion years from now. The two galaxies will pass through each other. Gravitational interactions will distort both galaxies, pulling out long tidal tails of stars. These tails will stretch for hundreds of thousands of light years, rivers of stars streaming through space. The ordered spiral structures will be disrupted. The disks will warp and buckle. Star formation will explode as gas clouds collide, creating brilliant bursts of blue light from newly formed massive stars. After the first passage, the two galaxies will separate again, moving apart due to their velocities, but gravity will slow them down, stop them, and pull them back together. A second collision will occur, then a third. Each collision will further scramble the stellar orbits and consume more gas in starbursts. The simulations show it typically takes about 3 to 5 billion years for the merger to complete after the first encounter.
During this time, the two galaxies will repeatedly pass through each other, each time looking different, each time more chaotic. The supermassive black holes from each galaxy will sink toward the center of the merging system through a process called dynamical friction. As a black hole moves through a sea of stars, the stars behind it are gravitationally accelerated, stealing momentum from the black hole and causing it to slow down and sink. Eventually, the two black holes will form a binary system, orbiting each other while surrounded by stars. The orbit will gradually decay as the binary emits gravitational waves, carrying away energy and spin. Finally, in a cataclysmic event lasting perhaps just a few minutes, the two black holes will spiral together and merge. The merger will release more energy in gravitational waves than all the stars in the observable universe emit as electromagnetic radiation during the same time. The space-time around the black holes will oscillate wildly, creating powerful gravitational wave signals that will propagate across the cosmos at light speed. If human descendants are still around and have gravitational wave detectors, they'll record this event with exquisite precision, learning about the masses and spins of the merging black holes and testing general relativity in the most extreme conditions. The end result, several billion years after the first encounter, will be a giant elliptical galaxy. Milky will contain roughly 1.5 to 2 trillion stars, nearly all the stars from both parent galaxies. Some stars will have been ejected entirely, flung out at high speeds by close gravitational encounters. These intergalactic stars will wander through the void forever, separated from any galaxy. But most stars will remain bound, settling into a roughly spherical distribution. The merged galaxy will be one of the largest members of the local group, dominated by old red stars with little ongoing star formation. Andromeda's existence isn't an isolated fact. It's part of a larger story, the story of how structure formed in the universe. In the beginning, just after the Big Bang, the universe was remarkably smooth and uniform. Tiny quantum fluctuations during inflation created slight density variations, regions that were very slightly denser or less dense than average. These variations were incredibly small, only 1 part in 100,000, but they were enough. As the universe expanded and cooled, gravity amplified these small variations. Denser regions attracted surrounding matter, becoming denser still. Less dense regions lost matter to their surroundings, becoming voids. Over millions of years, the first structures formed. These were dark matter halos, gravitationally bound clumps of dark matter. The dark matter couldn't collapse further because it doesn't interact electromagnetically. It doesn't radiate energy away. But normal matter, hydrogen and helium gas, could cool by radiating. The gas fell into the dark matter halos and eventually collapsed enough to form the first stars. These first stars, the hypothetical population 3, were probably massive and short-lived. They exploded as supernovae, enriching the surrounding gas with heavy elements. Subsequent generations of stars formed from enriched gas, creating population 2. Gradually, these early stellar systems merged together, building larger structures. Small galaxies merged to form bigger galaxies. Some of these mergers spun up rotating disks, creating spiral galaxies. Others created ellipticals. Andromeda formed through this process. It assembled over billions of years through mergers and gas accretion. The evidence is written in its structure, in the stellar streams from disrupted satellites, in the mix of stellar populations, in the warped gas disk. Andromeda is still growing, still consuming smaller galaxies. Over trillions of years, structures will continue evolving, though at an ever slower pace as the universe expands and galaxies become isolated. In a sense, Andromeda is typical. It formed, like most galaxies, through what's called hierarchical assembly in a universe dominated by dark matter. But it's also special to us because it's nearby. It's close enough to study in detail, yet far enough to see as a complete object. It gives us insights into galaxy formation and evolution that we can't get from our own galaxy, where we're embedded inside and can't see the whole structure. Andromeda is a laboratory for understanding how galaxies work. We've covered an immense amount of information, but let's step back and reflect on scale. Crossing Andromeda at light speed would require 220,000 years. The total number of worlds throughout the galaxy might be in the tens or hundreds of trillions. The galaxy has existed for about 12 billion years, forming shortly after the Big Bang. It will continue existing for trillions of years to come, though eventually merging with the Milky Way. Now think about yourself. You're a human being, approximately 2 meters tall. You live on a planet about 12,700 kilometers in diameter. That planet orbits a star in a galaxy of hundreds of billions of stars, and that galaxy is smaller than Andromeda. You're separated from Andromeda by 2.54 million light years, a distance so vast that the numbers lose meaning. Yet here you are, aware of Andromeda, able to contemplate its existence, to measure its properties, to understand what it is. This is extraordinary. The universe is vast beyond comprehension, yet conscious beings exist within it, able to understand it. We're made of atoms forged in stars. We're star stuff, as Carl Sagan said. The carbon in our bodies, the oxygen we breathe, the calcium in our bones, all of it was created in stellar cores and scattered through space by supernova explosions. We're literally made of the same material as Andromeda. We're not separate from the cosmos, we're part of it. Andromeda's scale is humbling. It reminds us how small we are, how brief our lives are compared to cosmic timescales. But it also inspires wonder. The fact that we can study something so distant, so large, so ancient, speaks to human curiosity and ingenuity. We've gone from thinking the universe was just the visible stars above our heads to measuring galaxies millions of light years away. That's an incredible achievement. Understanding Andromeda changes how we see ourselves. We're residents of a medium-sized spiral galaxy in a local group of about 50 galaxies. Andromeda is our largest neighbor, and we're gravitationally bound to it. In a sense, Andromeda is part of our cosmic neighborhood. The atoms that currently reside there follow their own evolutionary paths, shaped by the same physical laws that govern our galaxy. But on human timescales, Andromeda is distant and separate. We can observe it, study it, admire it, but we can't visit it. The distance is too great. Even if we developed technology to travel at significant fractions of light speed, the journey would take millions of years. It's effectively unreachable. This isolation is sobering. The universe is filled with wonders, but most of them are forever beyond our grasp. We can see them, measure them, understand them intellectually, but we can't touch them. Yet there's beauty in this isolation. The universe isn't a small, cozy place where everything is accessible. It's vast, filled with countless galaxies, each containing billions or trillions of stars. Andromeda is just one of roughly 2 trillion galaxies in the observable universe. Each galaxy is a world unto itself, evolving over billions of years according to the laws of physics, and we, from our tiny corner, can observe them all. We've journeyed 2.54 million light-years tonight. We've explored this immense galactic structure. We've examined its spiral arms, central bulge, supermassive black hole, and halo of dark matter. We've seen how astronomers measure such vast distances using the cosmic distance ladder. We've explored the lives and deaths of stars within the galaxy. We've discussed magnetic fields, cosmic rays, and the various types of nebulae that light up its structure. We've compared Andromeda to the Milky Way and found it larger but similar. We've examined its satellite galaxies, being slowly torn apart and absorbed. We've looked at gravitational dynamics and orbital mechanics that keep this vast structure stable. We've contemplated the possibility of life among its trillion suns and countless worlds, even if we may never be able to confirm it from our distant vantage point.
The true scale of Andromeda isn't just about numbers, though the numbers are staggering. It's about what those numbers represent. It's about complexity and diversity on scales beyond human comprehension. It's about a structure so vast that light takes longer to cross it than humans have existed as a species. It's about a trillion opportunities for stars and planets and maybe life. It's about a dynamic, evolving system that has been forming stars for 12 billion years and will continue for billions more. Andromeda is out there right now in its own present moment, even though we see it as it was 2.54 million years ago. Stars are being born in its spiral arms at this very moment in the galaxy's reference frame. Massive stars are exploding as supernovae, seeding the interstellar medium with heavy elements. The supermassive black hole at the center occasionally flares as it swallows gas or an unlucky star. Satellite galaxies are being torn apart by tidal forces, their stars joining Andromeda's halo. Gas is flowing, dust is forming, cosmic rays are accelerating through magnetic fields. All of this is happening now in Andromeda's present, a present we won't witness for millions of years. When you look up at the night sky and find that faint, fuzzy patch in the constellation Andromeda, remember what you're actually seeing. You're seeing the combined light of a trillion suns. You're seeing photons that have traveled for 2.54 million years through the void of intergalactic space to reach your eyes. You're seeing a structure larger than almost anything else in our local universe. You're seeing our cosmic neighbor, a galaxy bound to us by gravity across the vast darkness of space. You're also seeing a reflection of ourselves. Andromeda and the Milky Way are similar galaxies, born from similar conditions in the early universe, evolved through similar processes over billions of years. What we learn about Andromeda tells us about our own galaxy, and, by extension, about how galaxies throughout the universe work. We're all made of the same matter, governed by the same physics, sharing a common cosmic heritage stretching back to the Big Bang 13.8 billion years ago. The fact that we can understand Andromeda at all is remarkable. We evolved on a small planet. Our brains were shaped by the need to find food, avoid danger, and navigate social relationships. Nothing in our evolutionary history prepared us for comprehending structures millions of light years across, containing trillions of stars. Yet here we are, able to measure Andromeda's distance, map its structure, determine its composition, and predict its future. That's a testament to human curiosity, to our drive to understand the universe we inhabit.
If you found this exploration meaningful and these peaceful journeys through space help you unwind and drift to sleep, there are more cosmic stories waiting just a click away. I'll see you there, under the stars. Sleep well tonight, knowing you share this cosmos with something as magnificent as the Andromeda galaxy. And remember, every time you see that faint smudge in the sky, you're looking at 1,000,000,000,000 suns shining across the incomprehensible void of space, a monument to the universe's scale and creativity, and the long, slow dance of gravity and gas and stars across billions of years. Good night.